Hello, welcome back. Can all you guys hear me? You can use chat box to give me a response saying that if you can hear me or not. See. Yes, perfect. So let me wait another half minute so everybody will log in. So we have 22 people logged in. We're supposed to have 40. So today I hope everybody will be here and listen to our TA's orientation and explanation of what we are going to do in the rest of the semester for their labs, okay? So Derek and Jairo will present a set of slides to explain what are the rest 3 labs and the final project and what's the requirement. So after that, we're going to finish up the rest of the time until 3:45, talking about PID, okay? So PID is better than the PhD. Do you remember? Okay, so let's spend more time on the PID today. So I have 27 logged in. I'm going to pass the control to Derek. Are you there? Or Harold, maybe you can unmute yourself.
Yeah, Professor.
Oh, while waiting Harold. Okay, sure, no problem. Maybe Harold have some technical difficulties. You know, I have multiple people who are using this, and I upgraded my plan for the internet access. So now I have 1 gigabyte bandwidth, I guess. So, but I'm going to turn off my video to save bandwidth, okay? And let me see. Yeah, maybe I text Jairo to see. What's going on there. Okay, so let me see. You see, oh yeah, he's here. Jairo,
Hi, Dr. Chen.
it's your time and Derek's time to. You can share the screen and show the slides. Explain to the class about the rest of the labs.
Okay.
And you can take your time. Don't go so fast. And then we give time for students to ask some questions, as well as the TA office hour. My office hour will be put from the CAT course in the Zoom button. So you can press the button and log in and talk to me. So, Jairo, can you hear me?
Yes, I can hear you.
Very good. So now you can start to talk. I share your screen, or Derek, yeah.
Can you see my screen now?
Yes, we can see. By the way, I'm recording the whole session, so if anybody not here and still can watch this, okay?
Okay.
Go ahead.
Okay, so Good afternoon, everyone. Today, the purpose of this lecture is explain you how we are going to change our lab, considering that we are working until before the spring break on more mechatronic and more circuitry applications. I mean, more practical stuff using the Mesa box. But considering in this case the COVID-19 issues, we have to switch a little bit the way that we are working with the mechatronic course. So, can you see my slides?
Can you full screen that, Jairo?
Yes. Yeah.
Or presentation mode?
Mhm.
Okay. Okay. I'm going to. No worries. Making some. Okay. Let's stop here, and I'm going to share screen again. Okay, now you see the slides?
Yeah, I think we've seen the slides, but it'd be helpful to make it, put it in presentation mode. So like in the bottom right-hand corner, yeah.
Yeah. Yeah.
Okay.
Okay. Nice.
Okay. Okay. Excellent. So for today we have this outline. The first one is the effects of COVID-19. Basically, now we switch to remote learning. No more MesaBox-based laboratories. Based on that, we will have 3 new labs, lab 6, 7, and 8. Basically, these labs will be switched a little bit from hardware to MAD methodology, modeling, analysis, and design. How to apply this methodology using the computational tools like MATLAB Simulink. In this case, applied for mechatronic systems, but for sure could be extended to many other different systems. Also, we are going to explain you which are our lab expectations. I mean, how to complete all the lab assignments. How is the general guidelines for this new remote learning experience. We're going to show an example how we expect the reports from this point. Also, we are going to discuss about the final project for the mechatronic laboratory. In this case, this final project is a comprehensive exercise where all the MAD methodology will be applied for a specific control system. The deliverables for the final project and space for your questions in this case. Which questions you have about this new stage of the lab. Okay, so basically in our previous lab program, as you can see here, we was working at the beginning lab 1 and 2 with the scoreboard arm and its mechatronic application. In the second part, we start introducing the Mesa box, circuitry foundation, Arduino coding, SKI project. Basically, we stop in lab 5. From the lab 5 to the final labs, lab 6 to 9, basically we focus more on signal processing, controller design and its implementation using the Mesa box elements. This will be our original or previous lab program. However, from lab 5, we have to switch to a new program lab. In this case, this new program lab, basically, we are going to keep all the previous work that we made, but lab 6 to 9, we are going to be based on MAD methodology, modeling, analysis, and design. In this case, the application in particular, mechatronics systems. However, we are going in this case to go further, and this methodology could be extended to any system. In that sense, in order to keep an structure for this lab, we are going to use the tutorials from the CTMS website from University of Michigan. Let's go through the website in this case. Okay, basically here, this is the CTMS website. Probably you go through this website before. As you can see, this website is called Control Tutorials for MATLAB Simulink. We have here some introduction concepts like dynamic systems, dynamic response, the part of modeling. For example, here is the modeling of a system and code that's required to implement systems in MATLAB, for example, to implement the transfer function and make some modifications, RLC circuit, and many other important concepts. For our case in Mechatronics lab, we are going to focus in three of these examples: in the motor speed control, click here, motor speed, for example. As you can see here, we have like a matrix distribution. For example, I click motor speed. We have some tabs: modeling, analysis, control. In this case, we have different techniques for control: PID control, root locus controller design, frequency domain design, state space, and digital implementation. Also, we have another tab that consider modeling and control, but using Simulink instead MATLAB code. Both of them are important and will be very useful for you when you wanna perform the MAD methodology and modeling and design any different control system that you wanna do. For example, if we go, for example, through modeling here, we can see the model of the motor. We can go here, we can see the parameters that the website defined for this motor, the values of resistance, inductance, torque, electric resistance, all the parameters. The constitutive equations in order to derive the differential, the ODE that explain the dynamic of the system, how to derive the transfer function for this system in particular, which is in terms of speed and input voltage. Also, how to derive the state space model. And in this case, how to make the modeling, how to build the models using MATLAB Simulink. Also, you can go through analysis. In analysis, you can analyze, for example, the open loop response, for example, a step response using MATLAB. Also, you can do root locus or pole zero map for this transfer function that we are using in this case. We can compare different different responses if we change some parameters in this system. Also, we can make some tests for different inputs, not only step response, could be sine waves or could be impulse response. It depends of what the problem is asking you to do. Also, here we have the control part. In this case, we have the PID tab. In this case, the PID tab is based on the previous modeling made in the tabs of modeling and analysis. How to make the closed loop, in this case, to regulate the speed or the velocity of the motor. In this case, we have the plant that we find before the controller, that is transfer function of the PID controller. How to implement the transfer function of the model, how to derive, for example, the simple controller that is proportional control, how to calculate the step response for that controller, how to make some analysis for the system. In this case, how to design a compensate, how to design the proportional gain in this case, using all the MATLAB, all the tools that MATLAB has in this case. Here we have the PID control. Here we implement the PID control, in this case, the tutorial, how to tune in the gains, how the change affects the performance of the system. You are going to go through all this stuff during your lab assignments in order to understand all the steps of MAD, modeling, analysis, and control. Finally, I mean, you can go through all the other tabs as part of the required assignments for each lab. In this case, for Simulink, you can see here that we are going to do the modeling again. However, in this case, the modeling that we have is building Simulink totally. In this case, show step by step how to build the electrical motor, model. Dr. Chen, we have a question. Do we have a quiz for today?
We don't.
Okay, thank you. Here, how to build a Simulink model. Also, you can build using Simscape, that is a multi-body physics tools that has Simulink. We are not going through Simscape in the lab assignments. We are going only to the Simulink to build the model using the Simulink elements, not Simscape. So basically here, if you see this Simscape tab, you are not going through there in the lab assignments. All right, so you can do you will find basically the same for any of the examples that you have here. In this case, for the CTMS website, let's go back to the slides. We will have, in this case, 3 labs, Lab 6, Lab 7, and Lab 8. The Lab 6 is an introductory lab, comprehensive learning of MATLAB Simulink, in this case using the DC motor speed tutorial, that one that I showed before in the website. Basically, the due for all the lab assignments will be Saturdays. The Lab 6 is April 11, Saturday. Lab 7 is April 18, Saturday. And aircraft pitch control, the final lab, will be April 25. That is also Saturday. The idea is that you have plenty of time to work at each assignment. Right now, all the labs are available in CAD courses, so you can work in the labs at your own pace. Okay, so the Lab 7, we're going to switch the system to DC motor position servo tutorial. In this case, Lab 7, we are going a little bit further than in the previous one. Lab 6 is more comprehensive, how to learn how to use the tools MATLAB and Simulink in order to build all these models in the best way possible and make all the models work and represent the dynamic of the system properly. In the Lab 7, we are going to be more focused on, based on this modeling and analysis, how we can design our own controllers. And we are going through this with more details in the next slides. How we can find the gains for our proportional integral and derivative controller, our PID. We are going to define a methodology to do that. The final lab, MAD, aircraft pitch control, is a more comprehensive lab that basically combines all the modeling and analysis and also the design part for a more realistic system that is aircraft pitch control. That's the main idea or the structure of our labs for this second part of the semester. Okay, we have here some lab overview for the system. This is the student learning outcomes that we expect you could reach after finish these labs. Basically, understand the modeling and analysis of steps of MAD methodology applied in this case for the DC motor system. It means derivate the equation of motion, transfer function, or state space model for the system. Learn how to obtain step response, pole zero map, or root locus, and body plots for the system, which is really important to analyze the dynamic behavior of the system. Analyze the closed loop behavior using, in this case, the different controllers that you could find in the tutorial, P, PI, PID, and lag compensator. You will go through this. Learn how to obtain and create your Simulink models for these systems. I mean, if you learn how to build this system, you can later build whatever system you want. Final, analyze control system behavior, in this case using Simulink, not only the tools that we have in MATLAB, but also using the tools that we have in Simulink. All right, so for lab 6, modeling and analysis, lab 7, we are going to design. In this case, understand the design step of MAD. We are going to change a little bit the system. It's not speed control. We are going to position control. That is an extension of the previous system that we use. DC speed control overview, equation of motion, model reduction in this case for large poles. You will see how if we have a very big transfer function, we can reduce this function to maybe first or second order system that has an equivalent representation of the system behavior. Another important thing, understand the effects of PPI and PID control gains in your closed loop behavior. If you change the proportional gain, if you change the integral gain, if you change the derivative gain, you will see different effects on your closed loop response. So this is really important when you want to design a controller. Another important thing is introduce the pole placement methodology for picking the control gains. In your lectures of Mechatronics, you go through another methodologies. In this case, we are going to use this pole placement that is a model-based methodology. It means you have a model for your system first, second order, and you can reach, based on that model and some desired specifications, the proper gains of your controller to reach that desired state. In the lab, you will see a tutorial that we prepared for you in order to reach this methodology in the best way possible. Also, we have given system response requirement using pole placement to pick gains for PD, PI, PID controllers and compare the system response. I mean, in the tutorial, you will find some responses. You will obtain another response based on the pole place methodology, how the controller that the tutorial proposed compares with the controller that you find. That this is a really important part of control theory. How you ensure that your control met some specifications and in this case is better than other controller. How make this fair these comparisons is the fairest way possible. Okay, for lab 8, aircraft pitch control, the student learning outcomes will be apply the MAD methodology for a more complex mechatronic system, in this case, an airplane pitch. Be familiar with the state space and transfer function representations. Transfer function is one of the representations. State space is really useful also. So be used to employ both representations is important for you as future controller designers. Use Simulink to introduce disturbance and different reference input. I mean, what happens if your system is not perfect? If something goes wrong, what happened? How I introduce this undesired behavior and how I see how my system responds. This is the main idea on this lab. Use the state space and introduce, in this case, the disturbances that affect the system behavior. Okay. I think now Derek is going to explain the lab report formatting. And
sure. Yeah, so I can take over this part. I think you covered most of my other points on the other slides, but that's okay, Jairo. Yeah, so for the lab report, we thought we would add some structure. And so for the most part, we would like to see at least to have an introduction, so explaining like reason why we're looking at whatever lab we're looking at. And so the what, we'll have different parts. So someone's gonna be modeling part or the control part or Simulink. And then you want a conclusion. One thing we didn't put on the slides apparently is you should, before the conclusion or part of the conclusion, you should put a summary of things learned, things that you guys took away from the lab. And so we'll have a lab example report we can show you in a second. I did this in 2 columns. Can you go back to the slides really quick, Jairo?
Yes.
So yeah, the 2-column, it's not mandatory, but I figured because the final project is going to be in IEEE format, it's more of a stepping stone for you guys. So using this 2-column format will get you used to sort of structuring your paper, and then the transition to IEEE should be easier. For figures, when you guys put the figures on the paper, you should use a caption that should be descriptive or give you some information about what is going on inside the simulation. Traditionally, the caption is below the image, and for the folks that are using Microsoft Word, you can right-click your figure and then click Insert Caption, and that will allow you to put a caption, but it also auto-number formats all of your images. So it's a useful trick. Captions on tables, this should be above the table. I don't think we necessarily have any tables, but if you decide to put one in your report, you should put the caption on the top. And again, it should be descriptive. For images, make sure that it's not something that you can, you don't have access to a digital version. So like if it's in a physical thing, I don't think we want to see a picture of a graph from a screen attached onto your report. So if you have the digital copy, make sure that you save it to PNG or SVG or whatever format and input it into your Word document. Yeah, so if there's no questions on that, we can take a look at the example report real quick. Jairo?
Yes.
Can we switch over to the example? Yeah, there we go.
Mm-hmm.
Yep, so this is an example of the tutorial on the cruise control. And so we have an introduction part. Of course, you're gonna have your first last name on the top. We put the summary of learning outcomes in the beginning, and then we'll go ahead and we added information like diagrams of the car to show the system model, so calculate the transfer function. And then we went down and we went through all of the things we've asked you guys to do, at least for lab 6 on this example. And so we've plotted everything, added figures, and it looks like a lot, but I think for the most part, it's just using MATLAB and Simulink. And so it's mainly to get you familiar with using these control tools that are available. Yeah, so I don't know if all of this is up on CAT courses. So if you guys want to take a look at it and you have other questions, let us know at the end. Yep. So I think we're good here. Template for IEEE. Yes, there is a template. I have attached a link to the final project write-up that puts you towards the IEEE website for conference proceedings. And I felt like that one worked a little bit better than, or at least the formatting is not as tough as the article versions. So that's on the final project write-up. Yeah, it has both doc and LaTeX for those that like to do LaTeX.
Oh.
Very good. Do you guys have any questions? So Jairo, and I think we need to highlight another potential and technical difficulties regarding the Internet Explorer.
Okay,
Yeah.
this is the
Yeah.
next.
That's a
that's
warning. We need to give this warning in advance, but otherwise everybody will get very frustrated.
Yeah, we're gonna we're going through that, I think,
please,
as an example.
Yes.
So let's go to the next slide, please. Okay, so for the final project, we've added a list of 3 projects that you guys can choose from.
One.
Yeah, you'll choose one of these 3 projects, and they're going to be challenging, but it's meant more for you guys to try to apply your skills you learn in the MATLAB and Simulate portions of Lab 6, 7, and 8 to more real-world problem where you might face things like what happens when your sensor breaks, or if you have backlash in a motor, which is essentially some dead zone or other thing that prevents the actuator from actually moving the system, or there's a bit of error in the movement that gets as a result, or things like reactions, right? These can all be difficult things to model or even control. And so we picked 3. One of them is this tank level control, which is in the bottom left. And so if you have a pump, we're pumping into one tank, and we have another tank that level is producing some pressure and pushing into, let's say, tank 2, and you have another pump. How do we sort of control maybe what happens if tank 1 loses a sensor and we can only measure tank 2, or vice versa? That's going to be what is going to be explored in the tank level control. For number 2, the ball and plate, this is similar to an inverted pendulum problem, except for we want to balance this ball on the plate, or we want to have some control, like maybe the desired distance d. We can find some location that we want this thing to go. And so how do we control that? Also, you deal with things like integrator windup here. So when your sensors saturate, or there's a lot of error over time, how does that affect the system? Number 3 is more of process control, but we felt like it was more suitable problem related to everybody's skill level. And so this one has a reagent. You want this the pH of the system to maintain at a certain level, and how do we adjust the reagent so we get the proper effluent mixture coming out? And so that's the questions we're going to come into contact with on that problem. I think Jairo is going to show, so, well, from these 3 problems, the website that has the examples and some of the systems is quite old. And so some of the techniques they use to embed the simulations into the browser are dated. And so Jairo has found a way to bypass this. And so we're going to show you what that looks like. And so this is at the Newcastle website. So I'll let Jairo maybe explain this part.
Jairo, are you there?
Yeah, I'm
Okay,
here.
good. Excellent.
So basically, this is the website, control system design of Newcastle University. This is, I basically click this link that you find in the slides. If you go here through interactive, you will find the study cases that they have in the website. Here we have the tank level control, one of the related projects, ball and plate, and also pH control. Those are those 3 that we choose for you. You can choose one for the final project, as Derek mentioned before. For example, I'm going to click this tank level control. Here you can see the description of the system. Okay, the physical model prototype that they have. I'm going through the next part. Here you can see all the modeling of the system. In this case, the modeling is a little bit challenging because the turbulent flux, if you consider turbulent flux, this will be a little bit more challenging. Here you can derive all the transfer function and state space for the system. And at the end, you will find an applet, Java applet simulation. This Java applet simulation basically is, as Derek said before, an MBIP an MBIP representation or simulation of the tank level system. However, this website is around year 2000, so this website used Java applets, which is a technology that is not currently supported by Google Chrome or any browser. Even Internet Explorer has struggled with that. So we figured out a way to run the applets. If you see here, this message said you don't seem to have Java enabled browser. So, okay, that makes sense. However, we have here something called an extension in Google Chrome called Internet Explorer tab. I'm going to press this button. Look, you see this warning message? Looks like really old Internet Explorer message for year 2000. So we said yes. Basically, you will see here, after you install this extension to your Google Chrome browser, you will see here interactive. It goes through the beginning of the website again. I'm going again, in this case, to tank level control. You will notice this here. It's important to say that we made a tutorial that you could follow in order to install properly all these extension and enable some exceptions in Java in order that you can run all these applets without many problem. We made a detailed step-by-step guide. This guide is directly on the final project document. You can follow this guide, and we hope that you could make work these Java applets. I'm going back again here. We go here. Okay, I open the website. In this case, because I'm running this website with all Internet Explorer, this is a really old technology called ActiveX control. We are going to set okay, run. Remember that in this case, set you cannot run, you don't have a Java enabled browser. Now here you can see this chart is enabled. We can set here start, and you will see that how the simulation is running. Of course, you can modify the simulation parameters using, when you push change parameters, you can change, for example, the type of the set point. If you want a sine wave, if you want a linear or nonlinear observer, how much noise you want on your measurement, which gains you want on your observer gain matrix. For example, I'm going to reduce this one and see what happened. Okay, now the simulation change. Here we can see the parameters. I can change also this square by sinusoidal.
Yeah, so the green curve here is your actual tank level of tank 2 on the right, and the yellow curve is your set point, just for reference. So the gain here is pretty low, so the green line doesn't converge to your set point in yellow. And so you guys can play around with this, I think.
Yeah, can you click the change parameters?
Mm-hmm.
So those observer gain stuff, you can play with it. However, in your report, you must get these two numbers with very logic step-by-step justification. It's theory supported. It's not try and error blindly.
Right.
All
So,
right.
go ahead.
In this case, we changed again. It tries to follow, the green line tries to follow a little bit more the reference, the sinusoidal reference. In the bottom, you could find, for example, things to try, change the observer type from linear to nonlinear, move the observer poles towards negative infinity. You can try many different things here to play with this tank level control. I know many of you use Mac. Also, we have a tutorial to run the applets, these Java applets with Mac. Both links are in the final project document, so you can run in both cases if you want.
So this is called IE tab. It's embedded within only with specific browser from Microsoft, or from Google actually, Chrome, right? So
yeah, it's a plugin for the Chrome browser. Correct.
Yeah, yeah, it's interesting. I didn't know this. There's such an option. Okay, so any other questions from the class? Let me see the chat box. So I want to thank both of you to explore all these options. So we have the lab looks like a real lab. At least you can see something moving. Okay.
Yeah, so here's the final project deliverables. And so it's sort of a reiteration of what we talked about earlier. But it's going to be a 5-minute self-recorded final presentation. So you'll mainly discuss, the significant parts of the project, issues you've had, like your design, your simulation, these sort of things. More details are in the prompt. It's going to be roughly 6 to 8 pages. Once you include images and things, I don't think that's very long in IEEE format. And we put the due date on the 11th. And so it's not Saturday. I believe it is the Wednesday. So this is the day of your final. So by end of day on the day of the final.
I think the final is 13.
Is it the 13th?
Yeah.
I think that's what the goal was, to set it as the end of day on the day of the final. So it leaves you
thank you.
Some time after.
May 11 is Monday. Yeah.
Okay, thanks. Yep, so we can change that and re-upload for you guys. Other than that, I think that's it. What's the next slide? The next slide is just questions. Oh, yeah, no, this would be the outline for the final project paper. So you have an abstract, mainly outlining everything that you did in a very concise way, and then you'll have your introduction, system modeling. You'll go through the MATLAB Simulink under an open loop setting, see how the system responds, if it's stable, unstable. Then we'll go into controller design. So if you're following their methodology or you want to try something that you learned from the labs, then that's where you would put that. 6 is your results. So what did you get from it? Was it comparable to the tutorial? Were you able to improve the results? 7 would include any challenges you faced. Maybe some of the stuff that you encounter in the final project is going to be maybe new to you, or maybe this stuff was a challenge to learn or pick up. Those things you put there. And then 8 would be just wrapping it up, conclusions on what you were able to simulate, and if you have any other things that you wanted to try with the system you chose. And we put references about 3 to 5 just to let you try to find other resources to help you understand the different projects. Inside the tutorial from the Newcastle website, They do provide some other references as well. I'm going to try to track down and see if we can get the book or something on CAT courses for you guys, but those could be potential references that you can use that are highly related to the system that you're looking at. Other than that, I think we're on to the question slide.
Yeah.
So. Israel is asking if there is going to be final exam, and yes, I believe you guys will have a final exam on that Wednesday. What we'll be doing with the Mesa boxes, no, I'm not. I feel like we're gonna have to wait and to return them at some point.
Yeah, we can. You can return next semester. Are you guys coming back? None of you coming back?
I think for those that won't be back and that will have the box, maybe we'll figure out a way to do a mail. Maybe that's the answer there. And for those that will be coming back, we'll just have a way to drop it off by next semester. Hopefully everything is back to normal by then.
Yeah, let's wait. Maybe the final solution is to mail back.
Yeah, that could be an option.
Yeah. And of course, I want maybe the university will create a FedEx or some ticket for you, so you don't have to pay. So.
Is it possible to do the exam after, or sorry, to make the exam or the project due after the exam?
I think the answer is yes. I have 96 hours of time to submit my.
Can we do, if it's Wednesday, is Saturday okay, or Friday?
Let me see, my final exam time is.
Because you still have to leave us time to grade and plug in numbers.
Let me see my final exam time.
The final project should be in the lab folder files.
Final exam time is May 13th. That's Wednesday. 8:30 in the morning until 11.
Yeah, so if we did Saturday end of day or Friday end of day, that'd give you guys a few.
Maybe Saturday end of the day.
Okay.
Okay, there's no big difference between that. So let's give them. So please, no more extension. So Saturday will be 16th, 14th, 15th, 16th. So.
All right.
Okay, so give them the final project submission 16th end of the day. Yeah,
we'll adjust that stuff.
Good.
The TA office hours, I don't think we really touched that, but we want to try to make everybody available at different times. And so I think currently me and Jairo are splitting Monday and Friday. So Wednesday and Friday. Wednesday 12 to 1. I'll have office hours, and then Jairo will do 1 to 2, and that'll repeat on Friday. The links are updated on CAT courses.
Yes, the links are in CAT courses for the
final project info should be already unlocked. I think it's.
Yes, we should give everybody access to all 3 labs and the final project as well.
Right now, they have access to all the materials.
Cool. Very good. Very good. Thank you.
Yeah, and I think, Dr. Jen, you've also adjusted your office hours as well.
Yes. Yes. I'll send out all the notification.
Screenshot. I tried to click on it earlier actually, and I was not loading for me. So we can double check and debug that while you guys have your class.
Okay, so thank you very much for all of you. Derek and Jairo worked very hard, spent hours preparing the change of the labs. So I believe we'll maintain our quality of learning. So thank you very much. You guys can sign off. You don't have to listen to the rest of the class.
Yep, no worries. Yep, thanks guys.
Okay.
Thank you.
All right. Thank you, Jairo. So what I'm going to do next is to review through the PID control. So I'm going to share my screen right now. So you're going to see my screen. So see my screen now? Yes. Okay.
Yes.
Excellent. So I told you that the PID with all the gain lumped in a bracket outside of the bracket. So now you have E, you have integration of E, you have derivative of the E. So all these you can see all keep all the unit the same. Say for example, you are doing velocity servo, then your arrow has a unit of meters per second, right? So then this is also meters per second. This is also meters per second. Makes sense? So then makes good sense to me to add together and you have a total KP in here. So this one is also called ISA form. ISA form. Let us try to recall what we learned last time. The key concept is the called, this is called integrator windup, okay? Integrator windup. So if I put a PID control, so the integration, if you have a saturation in the control signal here, so your output will, your integration term will be so high such that the U proportional to this will get limited. When the U is limited, your output is like open loop control, all the way integrating up, then come back. So it's very bad. After this several oscillations, it will become steady state error is 0. So that is no good, okay? That is no good. So this is called effect of actuator saturation, okay? But fortunately, there is a scheme that we should consider. It's called anti-windup scheme. So this is the signal you applied to the actuator. So you have saturation here. So you pull out these two signals and the difference multiply again, subtract from here. So it's not so easy to get saturated from this integrator. Then after we use this anti-windup scheme, the original without is this, with is like this. So you can see there's no such oscillation there. And then you may say, oh, can I do faster than this? No, this is already the best because you cannot do much when you are on saturated status. Is basically open loop, okay? So then you may ask, what is the role of this gain here? Imagine if T sub T, this one is infinity, then the whole term is 0. Then as if there's no such feedback in here. So this is called anti-windup feedback. So then we can see that for different gains, the bigger the gain, the smaller effect of the anti-windup, okay? So when the TT is very small, so its effect is very high. So you can see, you can use that TT to tune the behavior of that anti-windup, okay? For the rule of thumb, if you already decided what is a TITD, then probably a good choice is the geometric average. Square root of this one is called geometric average. of the two time constants to get a TT. Okay. Okay. But if you do not use PID, then you have half of the integration constant. Okay. So I hope this is very important part that you will never forget in your lifelong time in your career. That whenever you have an integrator in the loop, you always have saturation. You always have a saturation. Okay? It's not avoidable. You always have it. So therefore, you always need anti-wind-up saturation compensation here, so that you have something like this instead of you end up with this. Did I tell you a story about my PhD student, a former PhD student, who wasted 3 months in summer? And because of this behavior and his robot moving from A to B, in between the robot will spin randomly, sometimes spin several circles, sometimes spin many circles before it move again. That's exactly due to the integrator wind-up. Okay, the reason is because in the beginning stage, okay, your integration, your error is big. Your error is big in here. So accumulate all the error, and then it's easily hit the limit of the control authority. Okay? So that's anti-wind-up. In fact, anti-wind-up is actually very simple to see in the PID control. Anti-wind-up in the coding. So you can see this part, this part is the anti-wind-up. So this signal is before, this signal is after. So this U and V minus and divided by this one, it is exactly the term you have seen here. So this is U, this is V, okay? All right, so today we are going to learn something very important. We mentioned about, oh, how I can set up my controllers. So I said, oh, you use a Ziegler-Nichols tuning rule. So I said, hey, you do a step response. You measure delta Y, delta U. So you have a delta Y divided by delta U. This is KP is like a DC gain, okay? Then this is one parameter, and you have another parameter called theta is L divided by T. L is here is the delay, okay, the delay. And then T is from this step. This is the step, okay. So this is blue line is a step. Then you have a delay in here. This is tau. This is L. Then you have a inflection point in here. So that is giving you the capital T. There are code, MATLAB code you can use to automatically approximate get this KP and theta. Okay, with KP and theta, you use this table. This is called tuning table. It is invented by Ziegler-Nichols. Okay, but this is called step response method. Originally, Ziegler-Nichols invented the tuning method. Is not in this form, okay? So remember in here in the PID and the T, you can see TI is 4 times of TD. Can you see that? This is 4 times. This is a magic number, okay? This is a magic number. I have full understanding about this right now, okay? I challenged this. This is an assumption, okay? I challenged it, and then I published a paper on this to change this. But anyway, that's a topic of research. What if they are not 4 times? So, but this one is here is 1 is 0.9, a little bit slower. This is bigger. So you can see some trade-offs in here in this slide. Let's see. But this is one of the 2 methods for Ziegler-Nichols tuning rule. On the other hand, Ziegler-Nichols' original idea is called critical oscillation method. Okay, it's called critical oscillation method. Okay, So what's that? Let me tell you. So this is something new. We haven't talked about this in the previous lecture. So basically you say, oh, I got a system I want to control. I don't have my transfer function G of S. I want to design a PID control. How I can decide those controller gains. You previously we were taught saying, hey, give me G of S. Now the situation is, sorry, we don't have a G of S. Okay, we don't have a G of S. So what you can do is to play with the system, give a step response to see how the systems respond. So then you can use the step, you can use this one here. It's called step signal-based tuning. We explained last time, okay? This one, called step response method. But in reality, originally, Ziegler and Nichols both invented the method. It's called critical oscillation method. What he did is, he said, let us give a P feedback, okay? P feedback, proportion only feedback to the system. Then I tune this KP to a point. You can see the bigger you put, the system is going to be more and more unstable. So then until to a point that you have a critically damping case, it's oscillating. It's not decreasing, it's not increasing, it's just a sinusoid. So that's called critically stability is at the stability limit. It's critically damping. So then once you have that, you know what is your KP, that number, and you measure the oscillation period. So that period is called critical damping. So we should use this one. So this KCU is the, I'll run the example for you, don't worry. So KCU is you tune the KP bigger until to a point you see an oscillatory response. Then you stop and see what is your KCU. It's called critically damping. So this is called critical gain also. So you put half of the critical gain if you use a P controller. If you use a PI controller, you put 0.45 critical gain. If PID is 0.6 critical gain. But how to decide TITD? So these are based on measurement of the PU is called ultimate period. Ultimate period. So the ultimate period is just in time, okay? So this is also consistent with the time. The divided 1.2, so divided by 2, divided by A. Again, TI is 4 times of TD. Did you see that? So that's actually an assumption. I'll show you whenever I get a chance to show you. And so you may say that, hey, if system, you push the KP, if you push the KCU and the system oscillate, that's actually stupid. You may already damage your system, okay, by making the system critically oscillatory. So that's not good. We'll come back to this one, but before that, let's see another idea, okay? So another idea is, I said, yeah, that's not acceptable, using the very high gain, proportional gain, and push the system to the instability boundary, and to measure that frequency, make that frequency PU, the gain is KCU, so that's no good. So basically, now, later, people invented another method. It's called relay automatic control, relay feedback, okay? What does that mean is you put this unit into the closed loop. Then the closed loop will start to oscillate. The system will behave like this. Control is saturated. and output is something like that. So it's easier to measure the PU is the same the PU, and this is a 2H peak to peak. This is 2A peak to peak, but this 2A and 2H, you should use this magic equation, 4H divided by A, okay, to convert this one into KCU, okay. Why this is so? There is some theory behind it, but for now, you just say this is true because you do this type of relay, you are not going to damage your system, okay? So your system is oscillation in a very controlled magnitude A, so it's not so big. So by doing that, can you see this one? So this is a relay. You push this one to T, is a relay to do a test. Then the system will start to oscillate, okay, because of the relay, positive or negative. Then your control signal U will become this squared, okay, squared. Y is become a sinusoid, okay, sinusoid. So based on that, you can measure this type of ratio and use this formula and use this tuning table. So this is called the relay-based tuning, okay? Or ultimate frequency PU, ultimate time period PU, and ultimate critical gain KCU, okay? KCU. So the benefits of using this relay instead of pushing the proportional gain to the limit is this is widely used in industry already, okay? It's easy to use. You have one button tuning and easy to explain to the user and works well for standard loops, and you don't need the prior information, very robust. You can get this system. So basically you push a button, then it's a relay test, then you record data and extract the information, look up a table, put all the coefficient into the PID, then you turn this one back for automatic mode. So then you can just get this PID tuned, okay? But sometimes you may say, oh, I want to retune it. Doesn't matter, it come back again. So the oscillation of Y is not going to be at the instability boundary. It is under the relay feedback. So the relay output is either positive or negative. So the U is my control. So it's like square wave, okay? Square wave. So this can be automated. So this is called relay-based automatic PID automatic tuning. So I hope you have heard about this. So let's run through an example, then will be nice, okay? Can you see the example? I think you can. Let me see. Yes, you are seeing this. Let me see. I'm still recording, I guess. So you can see this is a Simulink system. So basically this is called a 3-tank process. You guys will go do a lab on the tank control. So here is a tank using a pipe cascaded to another tank, cascaded to another tank. So I want to make sure the last tank will have a desired height. The control will be giving a control in here. So I measure the height, refer to my step, okay? And so we will see. So what is the control? I do a proportional control 300 in here. So this is my proportional control. I increase the proportional control gain. You will see what's going to happen. You increase it, it will start to oscillate. Okay, so then I measure what is my PU here. Okay, PU is 12, and 2H is here. is 2H is, is 1, and 2A is here, okay? 0.8, peak to peak, okay? Because we introduced, so this is what we have. So we introduced the result in here. This is the KCU will get this number. We're going to use a PID control. We can use the PID tuning rule we just learned here. This is the PID tuning rule, okay? With that, we'll be able to, so this is, we'll be able to do the closed loop control. So the step response is very nicely, okay? And the step disturbance is something here. We call these are the disturbance. We assume we added water in this tank, then this tank will get, the level will change. So, okay, so this is called disturbance rejection. So you always come back, okay, come back after you injected some of the flows there. So in PID tuning, and in the rest of a few minutes, and I'm going to show you that there are choices like you're using P, using PI, or using PID. All these questions we need to address, especially when you work in the industry setting. You need to talk about reliability issues, field tuning issues. So when to use a P control? Of course, P control for type 1 system, you will have a steady state error. You have learned that. So for the fast processes, some of the offset is allowed. Then this is okay to use P controller, okay? Like flow control, level control, okay? Sensor actuators are using orifice and for some flow control valves, okay? And level controls. The DP is a differential pressure cell and the current and pressure converter. So when to use PI control, this is the most popular one. So the process is not sluggish, but offset-free operation is required. Okay, so zero offset-free means zero steady state error. For example, the pressure control in distillation, that must be tightly controlled without bias. Okay. So when you use PID control, if you have a sluggish system, I want to make it to respond faster. So then I especially you have larger delays, it's preferred to use a PID, okay? But when you use in D, you have problem of a noise. The D differentiation will amplify the noise, okay? So the PID is widely used in the temperature control for furnaces, where you have a large time constant. In large constant means it's sluggish and slow. And you have transportation delays, okay? It's in the chemical systems. PI or PID control. But sometimes people using a dead time and time constant ratio. If your dead time and time constant ratio, i.e. the ratio is less than 0.5, use PID, greater than 1 is PI, and greater than 1 is a PID. So these are just a rule of thumbs, okay? So there's a comparison of this deck of slides, and so today we don't have any quiz, and we just hope you are going to find time to go through all the slides for the PID module. From next lecture, I'm going to do digital controls. It's quite important, and digital control definitely is part of the final exam. So I'm going to pause for some possible questions if we may have. You can type or you can just talk, okay? stop sharing and let's see. Can we do it on Simulink? Yeah, you can. Yeah, yes. So I don't care if you use Simulink or MATLAB. Okay. Sometimes MATLAB is easier. Sometimes Simulink is easier. I like Simulink. So if you do not give me a question, I'm going to count 3, then I'm going to end the meeting. Any advice on the debug Simulink errors? Yeah, that takes some time, okay? It takes some time. Usually you click help to see whether you can get through. If you got stuck there for too long, I suggest you ask those questions in office hour or in lab TA's office hour and share screen, get it fixed. Okay. In digital language, we should learn digital language 166, and they had us learn binary. So those digital controls, I don't need you to know anything about the number basis. But 166, you have digital circuits. Yes, you need to learn those digital circuits, logic circuits, MCUs, microcontrollers. But for digital control, it's different. So it's just a discrete time, it's sampling, and so on and so forth. Okay, so any other questions? I'm reading. Yeah, don't worry. Yeah, you can access the office hour form within CAD course. I'll put schedule there. You click that button, you reach me. TAs will post their own personal Zoom meeting link and a time, so you can reach them at that time. So we already designed those times, so you can access whenever you have. Or you have special need, send an email for appointment. We can talk at one-on-one basis as well. Okay, so looks like we're running out of questions and time. So I'm going to end the meeting when I count 1, 2, 3. Goodbye and take care and see you Friday. Bye-bye.
Thanks.
Okay.